So as people are rolling in, I will get started. So thanks everybody for joining us for this Hydrogen 101 Challenges and Opportunities of Hydrogen as a Zero Emissions Energy Carrier webinar. My name is Mark Lee Wilson. I'm the Edmonton Region Hydrogen Hub lead. And the Hub is an alliance of organizations from the region, including the municipalities, economic development organizations, academics, and partners from our Indigenous neighbors, the provincial government, and the federal governments. And we're working together with industry and with industry partners, industry associations to accelerate the development of a hydrogen economy in the region. Before we begin, I would like to take a moment to acknowledge that Dr. David Layzell is coming to us from Treaty 6, and I'm located, and as well as the Edmonton Region Hydrogen Hub is located on Treaty 6 territory, a traditional meeting ground, gathering place, and traveling route of the Cree, Saulteaux, Blackfoot, Métis, Dene, and Nakota Sioux. So we really encourage everybody watching to reflect on the treaties and the territories and the treaties and the people where you live and work. This webinar, of course, is part of an ongoing series of the Edmonton Region Hydrogen Hub's webinar that is meant to provide industry, government, and investors with the knowledge and tools to help them act on the unique competitive advantage in the Edmonton region for low-cost, low-carbon hydrogen production and adoption. You can see our past webinars on our website, erh2.ca. This presentation will be available tomorrow, so please be sure to share it with your colleagues, follow us on LinkedIn, Twitter, join our mailing list. Today's topic, Hydrogen 101. So we thought with all the new projects and pilots being announced and really a ramp up of interest in hydrogen and debates about production techniques and distribution methods happening every day, it's easy for even those of us that live and breathe hydrogen to get lost in the weeds of technical documents and economic analyses. So that's why we've invited Dr. David Layzell to help us take a step back and go over some fundamentals. Dr. Layzell is a professor and director of the Canadian Energy Systems Analysis Research Initiative at the University of Calgary, as well as the Energy Systems Architect and Research Director at the Transition Accelerator. Which is one of Canada's leading authorities on, David is one of Canada's leading authorities on the hydrogen economy, and his interdisciplinary research efforts have focused on exploring and defining transition pathways capable of moving Canada to a more sustainable future. This is the first of a four webinar series featuring Dr. Layzell. This one will provide a high-level understanding of the hydrogen opportunity. He'll be discussing the role of hydrogen in transportation in June and heating applications in the fall and hydrogen for exports in the winter. So be sure to sign up to our newsletter for registration details and not to miss out on those future sessions. Throughout the presentation, please put your questions in the Q&A box. It's right beside the chat box, so be careful not to mix those up. Use the chat box. Feel free to introduce yourself, where you're from, have some sidebar conversations. That's all great. But towards the end of the webinar, we want to leave time for questions and answers, and I'll be pulling those out of the Q&A box. There's also a feature in the Q&A box that will allow you to upvote questions that you want answered. So it'll be easier for us to triage those. So that's it for me. Over to you, David. Thanks very much for joining us today.
Thank you very much, Mark. It's a real pleasure to be here, and thank you for so many people to come on to having come on to this presentation. I'm going to share my screen and we'll get started. Here we go. What I'm going to be talking to you a bit about today is some of the challenges and opportunities of using hydrogen as a zero-emission energy carrier. We use hydrogen for a lot of things today in our industry, mostly to upgrade bitumen into synthetic crude oil to make fertilizer, nitrogen, etc., and to actually refine oil into gasoline and diesel fuel. But we're talking about using hydrogen as an energy carrier and essentially replacing gasoline, diesel, and jet fuel. I'd like to acknowledge three of my colleagues from the Transition Accelerator and the Alberta, University of Alberta, but Adnan was formerly with the Transition Accelerator. And some of the data they'll be talking about today has been data that has been collected and analyzed by them, working with me. So in the outline, I'm going to start by saying a few things about Canada's net zero commitment and the role that hydrogen plays in it. Talk about hydrogen as a transportation fuel, and go and look at the economics of hydrogen production and delivery before addressing the question about whether hydrogen is appropriate to be used for heat and power generation, and with a discussion about greenhouse gas emissions and some conclusions. So let's get started. As you know, Canada has made commitments to reduce its greenhouse gas emissions. The red line on this chart shows our actual emissions over the last 30 years since 1990. We've made commitments in the past. We've got our Kyoto commitment here and our Copenhagen commitment. We've not been very successful at meeting those commitments. We have bent the curve, but we haven't actually really achieved our greenhouse gas emissions and started to reduce our emissions relative to where they were back, certainly in 1990. And if we're going to address climate change, Canada and many other countries of the world have committed to net zero greenhouse gas emissions by mid-century. And this is really an understanding that certainly our climate impacts are becoming much more severe in the last 5 or 10 years. And a real recognition that we've got to stop thinking about incremental change and nudging our emissions down to transformative change, especially transformative change in our energy systems. And the reason energy systems are so important is that they account for about 80% of the greenhouse gas emissions in Canada. In 2019, this is a nice pre-COVID year, so we don't have the COVID effect in these numbers. But our greenhouse gas emissions from Canada are about 738 million tons of CO2, and over 80% of it, all of the blue and red pieces of the pie here, are the energy emissions, and they're all associated with our energy system. The biggest chunk of this shown here is really associated with the distributed combustion of fossil carbon-based energy carriers. And what we are talking about here is natural gas, gasoline, diesel, and jet fuel. And essentially, those, the greenhouse gas emissions from the combustion of those 4 fuels coming out of our chimneys of our houses, tailpipes of our cars, and various factories across the country, and the jet engines, of course, and airplanes flying, those emissions account for 334 million tons of the 738 million tons, something like 45% of our emissions. It's very clear that if we're going to reach zero emission by 2050, or by later this century, we need to switch to zero emission energy carriers. So when we actually are combusting and are extracting the energy from these energy carriers, we have no greenhouse gas emissions. What that does is that if we have emissions, it centralizes the emissions and makes it easier for us to address them. But ideally, we won't even produce emissions from the production of those energy carriers. One of the things that, by addressing these emissions, we also send a very strong message back to another major chunk of our greenhouse gas emissions in Canada, the fossil fuel recovery and processing sector, and the electricity generation sector, which need to be switching their attention to production of these zero emission energy carriers and reducing their emissions in the process of doing so. Now, there's not many options we have for zero emission energy carriers, and we could sit and talk a lot about it, but the ones that actually have the potential to make a significant contribution are very limited. Certainly the most important one is electricity. Electricity is, by its very nature, zero emission. When you consume electricity, it does not create an emission. The big issue is how we produce that electricity. And of course, we're looking at wind, solar, hydro, and some other like geothermal or tidal, as well as nuclear energy, could be a way of producing electricity without greenhouse gas emissions. Hydrogen is another energy carrier that, when it's produced or when consumed and energy is extracted from it, the only end product is water. And again, gives us that zero emission characteristic. Biofuels actually produce emissions at the end, but it's usually not counted as greenhouse gas emissions, because in the process through plant photosynthesis, and using the energy from the sun pulls the carbon dioxide out of the atmosphere to make the biomass. And that can either be burnt to provide industrial heat or even space heating for houses, or it can be converted into biofuels like jet fuel, et cetera, that can be used to support planes. Now, hydrogen is clearly in this, the way our analysis of it is probably the second most important zero emission energy carrier. Electricity is clearly the most important. And one of the benefits of hydrogen is that it can be used to back up and support some of the other zero emission energy carriers. For example, if there's an excess wind, solar, hydro, or nuclear that's beyond demand, one can convert the electricity into hydrogen. So you've got a way of making using hydrogen as a way of storing essentially electricity. And then if there's a shortage of electricity because demand is greater than supply, because perhaps it's the middle of winter, the wind's not blowing, the sun's not shining, one could actually use the hydrogen to make electricity. Hydrogen can also be used to greatly increase the amount of biofuels that one can extract from a given amount of biomass, and essentially conserve that carbon molecule and put energy into it that is embedded into renewable diesel fuel or gasoline or renewable jet fuel. So that's kind of, and then the last point here is in the process of hydrogen, is it can contribute to the resiliency of really what we are doing is making a new energy system. And we really want to make sure that that energy system is resilient to disruption, whether by, serious weather impacts or indeed war or other disruptions that could impact our energy systems. And more resiliency in the system is going to be really important in any design for any new net zero system in the future. Now, let's just talk a bit about what the markets are and the price targets for hydrogen. I think most of us know that on an energy basis, we pay more for transportation fuels than we do for heating fuels. And this is shown in this graph. If you look at the first 4 bars here, on the left chart here, we can see the dollars, Canadian dollars per gigajoule, that's per unit of energy on a higher heat basis, of what we pay typically in Western Canada for natural gas, or for, in this case, diesel fuel. Gasoline is in similar range as well. And this only goes from 90 cents to $1.50. And I think many of us think, well, we've been paying more than $1.50 lately. So in fact, this bar could rise up here a bit higher. And indeed, even our natural gas bar, we're probably a little bit higher here. One of the things that we're looking at is really see 2 different markets here. Potential markets for hydrogen. There's a market for hydrogen in transportation where, in order to be cost competitive with where we are today, we need prices somewhere between $5 to $8, maybe $9 a kilogram of hydrogen, which is sort of $35 to $55 or $60 a gigajoule. And at that price for hydrogen, we could be cost competitive with the fuel today, in part because a unit of energy in hydrogen, when put through a fuel cell vehicle, actually gives more transportation distance than when put through an internal combustion, when diesel, a similar amount of energy as diesel, for example, is put through a diesel engine. We'll talk more about a bit more about that later. The second market we're looking at is a much lower value market. And this is really to address heat production for heating, either space or industrial heating, or for power generation, for the heat that is going to be used to make the electricity. And we see a target market here in the range of $2 to $3 per kilogram, or 15, $14 to $21 a gigajoule. And this is, to make the economics work here, we really do need to start looking at carbon pricing for things like natural gas and home heating and other that would actually increase the price of carbon-based fuels, so that the zero emission nature of hydrogen is fully recognized. So let's talk a bit about hydrogen as a transportation fuel before we go into some of the economics of hydrogen production and transport. I mean, hydrogen as a transportation fuel is often you see graphs that look like this, where on the x-axis, we have the gravimetric density of various fuels, and that's how much energy is embedded within each kilogram of each fuel. And on the y-axis here, we have the volumetric density. In other words, how much energy is contained in each volume of the fuel. Now, the good news is that compared to liquid fossil fuels, gasoline, diesel, etc., per kilogram on this axis, x-axis here, you can see that hydrogen holds about 2.8 times more usable energy. These are all in lower heat values here than gasoline, diesel, jet fuel up in here. And compared to a lithium battery, per kilogram, hydrogen holds actually about 150 times more usable energy. So that's just compared to what's. So this is good news for hydrogen. However, that's not all good news. Hydrogen is a gas. So when you compare it on a volumetric basis, petroleum has, if you just look at hydrogen at room temperature and pressure, about 3,000 times more energy in a liter than a liter of gas. You can have a liter of gasoline or diesel. You got 3,000 times more energy of a liter of hydrogen at room temperature and pressure. When you compress the gas, the hydrogen, to a 350 bar, you still have 10 times more energy in petroleum. It's 6 to 7 times more when you go to 700 bars. And even if you take the hydrogen and you drop its temperature to 253 degrees below zero, that's in Celsius, or about 20 degrees Kelvin, the hydrogen becomes a liquid itself. And even then, it's still, there's hydrogen liquid right there. It's 3.8 times more to get a gasoline or diesel fuel up here. Not only that, that's a challenge. That's a serious challenge for using hydrogen as a fuel. And not only that, the tanks to hold the compressed gases, especially on these two, it's highly compressed gases, they weigh a lot more than a petroleum tank. Typically, a rule of thumb is something like if you want to hold 1 kilogram of hydrogen, you need about 25 kilograms of hydrogen tank to hold a kilogram of hydrogen. Obviously, you want to hold more than a kilogram at a time, but that's kind of the scale that we're talking about. But on the other side, as I mentioned previously, when you take hydrogen fuel cell electric vehicles, they require less fuel energy than internal combustion engine vehicles to travel the same distance. And so this is, here's an example of drivetrain efficiencies and some of the issues around 3 different vehicle types we can look at. Here's a combustion electric vehicle. It's sort of an internal combustion engine, uses a fuel, gasoline or diesel here. Internal combustion engine turns the transmission and drives the car along. A battery electric vehicle is nice and simple. It's you plug it in, you have power filling a battery, the electricity goes through an electric motor and drives the transmission. And a hydrogen fuel cell vehicle, you put hydrogen in here. The hydrogen is used, converts the fuel cell stack, converts the hydrogen into electricity. That can be used directly by the motor or go into a battery pack and used by the motor. These two also have an advantage of when the vehicle is slowing down, the motor can actually be run, if you like, run in the opposite direction. So the actual wheels are turning the motor faster and the electricity is not coming in, and you can actually put electricity back into the battery pack on both of these type of vehicles. This option is not available on internal combustion engines. So when you actually look at the key factors that determine the efficiency, the drivetrain efficiency, one is engine conversion loss. And in this case, battery electric vehicles here in the middle are a lot better than fuel cell electric vehicles. We'll show you some chart on that in a minute. And they're a lot better than the internal combustion engine vehicles. When you look at amount of energy that's used while idling a vehicle, in battery electric and hydrogen fuel cell electric vehicles, when you're idling, they basically just turn themselves off. Right away. They don't use electricity when they're idling. Whereas in internal combustion engine vehicles, we all know most of our cars don't turn themselves off when you pull up to a stop sign or parking, and they keep running and they're using fuel. Regenerative braking is another issue. Battery electric and hydrogen fuel cell electric vehicles, both, as I talked about before, have the capacity to use regenerative braking, to take some of that energy from the wheels and put it back into the battery. And so that gives them some real benefit over internal combustion engine vehicles. The other issue is energy losses at low temperature. An internal combustion engine vehicle in this case is a lot better. There's a lot of waste heat that comes off of these engines, and we can use it to basically keep all of the engine warm, but also heat the cab, etc. And so the energy losses are much better for, much lower for, because they've already lost the energy, if you like. So you don't lose more energy when in low temperature. And so that's better than a fuel cell vehicle, which is actually better than a battery electric. And the energy that's actually needs for heating, which is kind of tied to the energy losses, is again better for internal combustion engines and hydrogen fuel cell. So when you actually put all of this together, we see that the drivetrain efficiency is the lowest for gasoline vehicles. It's a bit higher for diesel vehicles. It's the highest for battery electric vehicles up here, and fuel cell vehicles come in around 40 to 50%. The overall converting of fuel energy into, I guess, a drivetrain efficiency would be mode of energy going out per unit of energy being supplied to the vehicle. And so what you note here is that when you're going to shift, if you're going to shift from gasoline vehicles to a battery electric vehicle, it gives you the largest efficiency improvement. You can see up to 4 times or more improvement in efficiency. Another reduction of energy use, pretty massive when you move from a gasoline vehicle to a battery electric vehicle. Moving from more efficient diesel engines, and especially on the big trucks when they're not stop and going, they're running at 90 kilometers an hour, 95 kilometers an hour on a highway. These engines are superbly designed to be incredibly efficient. And so therefore the drivetrain efficiency benefits you get from moving to either a battery electric or to a fuel cell electric are less than if you were using a gasoline vehicle. The big issue then, so let's see about what are the emerging markets for these various choices. We've got, so I've got 3 options here. The yellow vehicles here are electric. Hydrogen vehicles are shown in blue, and in some cases where we could look at possibly ammonia. Ammonia is a compound that's made from hydrogen. You take nitrogen from the atmosphere and you can make ammonia. It has some advantages and some disadvantages, but it's another zero-emission fuel that is often grouped in with hydrogen as an alternative. We'll talk a bit about it later. And then, of course, there's the biofuel option for transportation. Now, what I've got here is some of what I've been seeing in the literature and in talking with the various industry groups about what's the emerging market choices that are most attractive. For most light-duty vehicles, certainly battery electric makes the most sense. The only group right today that seems to be looking perhaps more at hydrogen electric or maybe taxi fleets or vehicles that are used very heavily, 20 hours a day, picking up, dropping off people, and they don't want to take the time out to recharge. They want rapid refueling. So things that really shift the more interest in fuel cell vehicles than battery electric are rapid refueling capacity, because you can refuel in 10 minutes or so, more similar to the speed of refueling gasoline or diesel. If you have very large fleets, and this is especially the case when you start looking at buses here or even the large truck fleets, very large fleets, when many of the companies that we've been talking with, they looked at, certainly they're interested in battery electric buses, and there's a real significant role for battery electric buses, certainly school buses and urban transit. But when you get to very large vehicles or very large fleets, where the infrastructure challenges in actually building enough infrastructure at a bus barn to recharge, say, 300 buses overnight, getting ready for going out the next day, that becomes a very huge logistical challenge and economic challenge. And so the rapid refueling and the ability to have fewer fueling stations becomes of interest. Longer distance and long shifts. This is certainly for trucking and for trains, and certainly for ships and airplanes. Long distances, long travels, you just can't put enough electric charge on. Off-grid operations, certainly in off-road operations, a lot of the discussions is they may not put a lot of kilometers on tractors, but when a farmer needs a tractor to plant or to harvest, these vehicles are being used essentially 20 hours a day. They're out there, they're in the spring season and the fall, very intensively used. The possibility of actually doing a recharge is challenging. There may be some battery swapping that in the future may help in that area. But right now, if we are going to go net zero, we're looking at probably biofuels or perhaps hydrogen for a significant portion of these fleets. Very large loads where battery weights compromise carrying weights. This is certainly an issue heavy duty trucking and others, even on buses, etc., where you have long distances, for example, on intercity and tour buses. I just can't put enough weight on to get it. And there's certainly a lot of interest and movement towards hydrogen in those applications, and really cold weather operations. And a lot of trials are being done in Edmonton now to just see how well battery electric versus hydrogen electric vehicles do, and whether there's how much of an advantage under cold weather operations. Ultimately, the market is going to decide where this is going. This is not going to be top-down control, but this is kind of where I'm seeing the markets shift out overall. Let's talk about the economics of hydrogen production and delivery. Now, Canada happens to be very fortunate. We're one of the, internationally recognized as one of the world's lowest cost producers of low carbon hydrogen, whether it's made from fossil fuels coupled with carbon capture and storage, that's often called blue hydrogen, or it's made from water electrolysis using very low carbon electricity like wind, photovoltaics, hydro, or nuclear. And you can see this chart here. This is from a Japanese study in 2018. It compares all the different countries on the Pacific Rim countries, and Canada down here using natural gas and CCS, estimated to be able to produce, and these I've converted this to Canadian dollars, but can produce hydrogen almost at about half the wholesale cost of diesel, 1/3 the retail cost of diesel, which is an incredible price compared to other jurisdictions. Hydro, we can produce, this is a few years ago, in provinces like Quebec and Manitoba, can produce the lowest cost green hydrogen probably in the world because of low cost electricity and lots of water availability, fresh water, and then they can be some of the lowest cost producers of low carbon hydrogen. So let's look at the components and the cost, because there's more than just the cost of production. There's also the other parts of the value chain. And I've put on here in the background the target prices that we have for target prices for retail prices for transportation between $5 to $8 a kilogram, $2 to $3 a kilogram for heating. And if you're making it from blue hydrogen, essentially from natural gas with CCS, if you have only $2 a gigajoule natural gas, one can make it about $1.60 a kilogram. That's including the carbon capture and storage. As the price of natural gas goes up to, say, $9, you're approaching more the $3 a gigajoule or a kilogram here, $3 a kilogram here price to produce it. In order to achieve that price with green hydrogen, this is with current electrolyzer technologies, we probably need 1 to 2 or maybe 1, 2, or 3 cents a kilowatt hour, 10, 20, or $30 a megawatt hour price. And that is really baseload, where you're actually using your electrolyzer essentially 90 to 100% of the time, and you can actually achieve and be competitive on this price. When you start using your electrolyzer a lot less, for example, you're only driving it off wind power, and so with maybe 34% efficiency on your wind resource or 34% capacity factor, you then the price goes up because you've got to pay for all that capital cost of your electrolyzers and compressors, et cetera, when they're only being used for 30% a third of the time. So then on top of that, say we're making hydrogen, and then we have to actually get it, process it and transport it. There's basically 3 ways to do this. And there's probably more than that, but there's the 3 main ways we're looking at here. One is to compress it into tanks. It costs a lot for the compressions, a lot of electricity required for the compression. You want that to be, of course, low carbon electricity, so it can be a little bit more expensive. And this drives the price up and adds another $2 to $3, even up to $4, $3 to $4 a kilogram. If you want to convert it into liquid hydrogen, which really makes it better for long distance transport, and you can bring more at a time, we can talk about, we're talking about adding maybe $4 or $5 a kilogram to the price, and depending on how far you have to move it. There's also a possibility of pipelines, but the challenge with pipelines is you really got to talk about large volumes. You're not going to move small amounts of hydrogen by a pipeline. So in our calculations here, we're based on 300 tons of hydrogen per day being moved 300 kilometers in a pipeline, and at least 8 tons a day being diverted on a side pipeline to go to a fueling station, for example. And the amount of that side diversion of the 5 kilometers at the end of your 300 kilometer run or 295 kilometer run affects the price pretty dramatically. So that's the processing and transport. And then if you're providing this for a fueling station, one also needs to build the fueling station and supply it. And so, and whether it comes by tube trailer, liquid hydrogen is the lowest cost here. You pay the most here, but you save money on the fueling station. And pipeline is the highest cost. You save money here, but you pay more on the fueling station. So obviously there's a balance here. And once, this is, everything here is about centralized production of hydrogen. It's processing and transport for use at fueling stations that will be distributed across the countryside. There is, this high cost, especially the high cost of processing and transport. And also the fact that we're talking in the early stages of building smaller fueling stations that have to then grow. This high cost of processing transport has really increased interest in on-site hydrogen production. By one of the most common right now is, of course, water electrolysis. You just use green hydrogen production. You're going to pay more for that, but you save the money on the transportation. And you can sometimes actually get some pressurized hydrogen out of electrolysis that saves some money on your fueling station. The other possibility is a lot of interest in methane pyrolysis, where you can actually take natural gas, convert it into hydrogen, and you make carbon black. It's a black powder, essentially, or that can be carted away. You don't have to deal with the carbon dioxide. There's a lot of interest in this. A lot of companies testing, not commercial, ready for commercial deployment quite yet, but hopefully maybe within a year or two. Now, let's talk about some of the analysis that we've been looking at is what's the minimum economic viability for fuel hydrogen without ongoing public support. You're going to need public support even to get to this stage to actually build the infrastructure and get the vehicles on the road. But what you don't want is to be able to keep paying year after year to keep the vehicles on the road. And excuse me, our estimate of that is we need about 4 tons a day for each fueling station, and ideally 2 fueling stations that are separated by 300 kilometers. We could think of this as Edmonton and this is Calgary, for example, or you could pick any other place in Canada or North America. And I've also looked at here where maybe the actual distance where the trucks are going are maybe 325 kilometers each way. So you're talking a round trip, or a truck that could start here, for example, drive down, drop off the load, refuel, and then drive back again. So they're doing 650 kilometers a day. And that would be, so let's think about what the scale and operations we need in order to deploy to get to this kind of a scale. Now, these stations at 4 tons a day, and let's say the carbon price or the price for the hydrogen price is $7 a kilogram of hydrogen, 4 tons a day, that's $28,000 a day. It's about $10.2 million per year for each of the stations. And that will help to pay for the cost of building the station, the cost of staffing it, and of course, a large price is the cost of the fuel supply to that station. The fuel use would be typically, and this is maybe a little bit conservative, it's about 100 grams of hydrogen per kilometer. These are for the heavy duty trucks. It possibly goes to 110 or 120 in some cases, may go down to 90 depending on the truck. But so for easy numbers, 100 grams of hydrogen per kilometer, 650 kilometers per day. So it's going to use 65 kilograms of hydrogen per day. Most of the vehicles, the hydrogen fuel cell vehicles that are being brought forward today, the early ones that are just coming into Calgary now, have only about 50 to 60 kilograms capacity on the vehicle. So you don't have enough capacity to run the full trip. So you're going to need to refuel, drive one distance, and then refuel quickly and get back again. In the future, we're probably going to see these trucks coming with liquid hydrogen on board, where they could hold perhaps 100 kilograms, in which case they could do a round trip without a problem. Without having to refuel, just refuel once at the start of the day and do the round trip. But right now we're looking at 2 refuelings per day is the model. Now, how many vehicles are we going to need to keep these stations going? Now, if the vehicles were running 7 days a week, 52 weeks a year, you'd only need 114 trucks for this whole system. But in reality, actually, it's more likely, and we put here that these vehicles would run 5 days a week for 50 weeks a year. So we're going to need 167 trucks to keep these stations going. That's kind of the scale of operations that we think is a really good full up, demonstration scale of what Canada needs, and we need to start deploying in regions across Canada in order to really get this hydrogen economy going. To put this number of truck in perspective, these number of trucks, Alberta has 110,000 Class 8 trucks on the road today, a little more than that, probably 115,000. Canada has about 500,000 Class 8 trucks on the road today. So we're talking about a lot of scales and fueling stations that would eventually be much larger than 4 tons a day, with many more trucks relying on those stations more or less every day to meet their fueling needs. Let's talk now about hydrogen for heat and power generation. And one of the questions that one of the issues here is to really understand about heat and power. You really can't do it by delivering hydrogen by tube truck or truck delivery. You've got to either make the hydrogen right on site and then put it right into a pipeline network that supplies houses, or make it exit right where you're going to use it for power generation. Or if you're going to be transporting, making it centrally and moving it, you need pipeline distribution in order to hit this price target. You're going to have low-cost hydrogen production and pipeline delivery at large volumes. All right. So for heat and power, you don't need, of course, the fueling stations. So the only way we're going to hit this target market, the target price target is with pipelines. But what I often get asked, and I think is a really good question, is why consider hydrogen for heat and power in the first place? After all, electricity-driven heat pumps, and especially for space heat we're talking about here, electricity-driven heat pumps are so much more efficient than furnaces, natural gas or hydrogen furnaces. And this is shown in the graph I've shown here. Natural gas furnace here, it's between 80 and 92% efficient. Hydrogen furnaces, they're just coming out today. They're also, you can have especially a condensing hydrogen furnace, you can get a similar efficiency of 80 to 92%, perhaps efficiency on the furnace. Whereas a heat pump, if it's 10 degrees Celsius outside, you're not using the energy to produce the heat. You're using the energy to take the heat from outside and move it inside. So heat is pumping heat from outside to move it inside. It cools the outside and warms your inside. As long as it's 10 degrees Celsius outside, you can get enough heat from outside and you can get 300% efficiency in the amount of heat inside compared to the amount of energy that you had to put into the process to move the heat. When you got ground source heat pumps, you can even get up to 400% efficiency. With air source heat pumps, as the temperature drops, the efficiency drops down. There's at 0 degrees, you're around 200%, minus 20, around, say, 150% efficiency. But it's still more efficiency in energy here. And so some of the reasons for why consider hydrogen here is, one is the seasonal variation demand. In Alberta, in Western Canada, Saskatchewan, Alberta, in parts of Northern Ontario and Quebec, you get about 8 times more demand for residential heat energy demand in January than in August. And so there's a real issue of, it's possible to store hydrogen a lot more easily than it is to store electricity. And so you either got to find a way of storing a large amount of electricity in the summer that can be actually picked up and used in the winter, because that's when you need it, or you need to find a way of building extra capacity that you only really use for electricity generation, you only use in the winter. And the real question is, what's the economics of this? And I don't think we fully got that analyzed in a way, at least, that gives me comfort that we know how to handle it, especially in provinces that don't have large hydro storage capacity. And I'm thinking Alberta and Saskatchewan, for example. The second issue is the issue of building retrofits. And what role building retrofits has in the movement of, say, residential sector to low carbon energy. And if this is some work that Hamid Ramanavard has been doing within the Transition Accelerator, looking at historically What is the how many houses are we building? These are our housing stock. And this is, I pulled out Ontario as an example here. We've done it for other provinces as well. But in Ontario, this is the increase in housing stock. And these are the number of new houses added in 2001 to 5 and 6 to 10, 11 to, and this is, the houses are decommissioned as they get older, they get torn down and replaced. And the decline here is the replacement of houses over time. And we've taken the historical data and projected into the future. In addition, we've added the new stock of houses that are being built right now, but they're still being built with old technology. They're being built with traditional natural gas furnaces. And those are going to need, if we're going to get to net zero, those are going to need to be retrofitted. And then eventually, we've got then what are the new stock here that is built with new technology, may be built with heat pumps, et cetera. And they will be coming on, and they presumably won't need to be retrofitted. So when you actually, by 2050, our analysis is across Canada, retrofits are going to count for anywhere between 65 to 85% of all new buildings. And the retrofit costs, when you're looking at retrofitting rather than new build, and it's the cost, I would argue, are a lot more for electric heating and going to heat pumps than for hydrogen heating. The cost of the heat pump itself is worth a lot more than a furnace. The increase in the electrical service to the building. Most houses that are, if you only got a 100 amp service, you want a heat pump, boy, oh boy, you got to have another 50 amp service. Which is that costs a fair amount. Then you've got to actually upgrade the electrical service into each of the communities to provide this electric. And then, of course, you need new generation capacity. Certainly, there's a cost to switching to hydrogen heating, but there's a lot of evidence that we can repurpose a lot of our existing natural gas infrastructure. And new low carbon hydrogen transmission and storage you're going to need that as well. And the question ultimately, I think, is I would say the jury's still out on what is the best strategy for Alberta and for Canada, for other provinces of Canada, to go on. I think a lot more study is needed in this area. Another couple other things that are important is the hydrogen pipeline infrastructure could really benefit if you're going to be putting hydrogen pipeline infrastructure, which you're going to need in order to do space heating, for example. It could really help to benefit other sectors. For example, heavy duty transport. Right now, we're really on the edge of being able to supply hydrogen to support heavy duty transport by using trucking for infrastructure. It's possible to probably just barely make the economics work if you get at large scale. But if you actually had a pipeline infrastructure that was already there for space heating, it would really help to reduce the cost of hydrogen going into heavy duty transport and speed the transition in that sector. Also for sectors like steelmaking, moving from blast furnaces using coke and coal to direct reduction of iron using hydrogen, that could be made possible. Other industry sectors that need high temperature heat, where heat pumps aren't going to work, we need high temperature heat. Hydrogen pipelines are going to be critical, and I would argue even peak power demand, and also this pipeline infrastructure that you'd be putting in to support space heating would also provide a low-cost strategy to get hydrogen from renewables to market, because a lot of our wind farms and solar farms and hydro facilities are obviously away from our cities, and one needs to be able to make the hydrogen there if you don't have a market for that hydrogen, and put it into a pipeline and get it to market. I mentioned right at the start about the resiliency, and I would argue that we really need to think very carefully as we move towards a net zero energy systems. What's the resiliency going to look like? And I would argue that electricity providing all energy services may not be an optimal solution if there's a problem with the grid. Hydrogen safety is another issue that I'd like to just talk briefly about. So how is hydrogen better than current fuels? It's non-toxic. It dissipates more rapidly than combustible gases if there's a leak. Its combustion product is non-toxic, like it doesn't produce carbon monoxide or particulate matter. Hydrogen leaks have little adverse environmental impacts. I'll say something really briefly about that in a minute. It's lower radiant heating when burning, which means that it doesn't catch other things on fire. It's a different color of the flame, if you like, in terms of it doesn't produce as much radiant heat. How is hydrogen worse than current fuels? this is the big problem, is that wider range of flammable concentrations in air, smaller molecules for more leaks through cracks. It's odorless, it's colorless, and it can cause embrittlement of steel. And there's a lot of mitigation strategies that can be used, rigorous standards for production, transport, and use of hydrogen. Widespread use of hydrogen sensors are going to be needed in a hydrogen economy. And you're going to have to add odorants for use in space heating, so people can smell it, but in addition to the sensors. And you need strategies to make the flame visible, which can be done. There's an example here. You might want to look for this on the internet. It's just two trucks of gasoline versus a hydrogen truck catching on fire, and it's I prefer to sit in the hydrogen vehicle. There's a sense that these are safer fuels for transportation. I'm going to go through quickly on this. Pipelining hydrogen compared to natural gas, methane, hydrogen's 2.5 times more energy on a kilogram basis. So that's good news, but on a liter basis, it's bad news. Same as what we talked about before. But hydrogen's a smaller molecule than methane, so it can actually move more quickly in a pipeline. So it can move actually almost 3 times more quickly in a pipeline with, given the pressure, et cetera. And so it can actually deliver in the same size of a pipeline, of a natural gas pipeline to a hydrogen pipeline. It can deliver about 85% of the energy delivered by natural gas. And that's good news. The problem is that the compression of hydrogen takes more energy, so it's more expensive. And hydrogen can leak more easily, so a lot more attention needs to be paid on seals and to making sure the hydrogen doesn't leak out of the pipeline. Most transmissions are made of steel that is not compatible with hydrogen, so it's an embrittlement problem, et cetera. And that's bad news, and a lot of work is needed in this area to figure out how we can maybe repurpose some of our existing infrastructure. The good news is that most of the distribution pipeline, the low pressure pipelines that comes to each of our houses, are compatible with hydrogen. And as a general rule of thumb here is if you want to move hydrogen 300 kilometers, you need demand of at least 300 kilograms of hydrogen per day. If you want to move it 1,000, you need demand of at least 1,000 a day. And that kind of gives you a sense of what the scale we need to use in order to get a pipeline infrastructure working. I'm going to just end on this brief discussion of greenhouse gas emissions. Here we have the green hydrogen chart here, and it's really driven by the carbon intensity of the electricity that's produced. And this is life cycle emissions of wind, nuclear, hydro, solar, and even biomass. Base that includes infrastructure costs to make the panels, solar panels, et cetera. And they come in at very low life cycle emissions here of 1 to 2 to 2.5 kilograms of CO2 per kilogram of hydrogen. It can be reduced a bit with improvements in efficiency of electrolysis. We might see going down to the shaded region here. In comparison, hydrogen from natural gas, if it's the way it's made today with steam methane reforming and no carbon capture and storage, we're talking hydrogen emissions in the, life cycle emissions in 12 or 13 kilograms of CO2 per kilogram of hydrogen. Some early stage steam methane reforming where you can get carbon capture and storage. The biggest problem here then is the methane emissions that occur upstream. That's the upstream methane emissions. And if you have a leak rate of 3% of your overall value, that's pretty high estimated rates, but that you're adding a lot of extra emissions well into up to 5 or 6. Where we need to get to is the true blue hydrogen. It's being built, Air Products is building ATR with 94% CCS. Hopefully policies will be implemented to reduce dramatically the amount of upstream emissions, getting it down to something like 0.5, and even capturing some of the upstream CO2 emissions. And that could get us down to, something that's comparable with where we are with some of the green hydrogen. And so there has to be policies and regulations and technologies deployed to get us to this kind of a carbon intensity for our hydrogen. The last thing I want to mention is just a bit on recent reports in the literature about hydrogen being a greenhouse gas. And the reality is that it's an indirect greenhouse gas, not a greenhouse gas directly. And here's the way it works. Essentially, we produce a lot of methane. It's a natural gas, essentially, as a main constituent in natural gas. There's human activities and natural processes that put methane into the atmosphere. The methane is removed from the atmosphere. In large part, about 80% of the methane cycle is removed by reactions with hydroxyl that produces and essentially gets it out of the atmosphere. So it's a potent greenhouse gas, but it's removed from the atmosphere. And this process keeps the half-life of natural gas in the atmosphere at about 12 years. In a hydrogen economy, there are always going to be leaks of hydrogen. And the hydrogen is going to, though, compete with this hydroxyl in the atmosphere produced by the sun in the atmosphere or in normal atmospheric chemistry reactions. And it will compete for that as hydroxyl and essentially pull that hydroxyl away from reacting with methane. And the result is going to be the methane won't be removed from the atmosphere quickly, and the half-life of methane will increase and have a bigger global warming effect. So this is one of the big concerns about hydrogen. However, if you do the analysis, the indirect effect on greenhouse gases is small, much less than 5%. For example, if you take the Canada's estimated 55,000 kilograms of hydrogen per day could be used in the hydrogen strategy for Canada as a energy carrier by 2050. So that's almost 30% of our energy system. That would, if we had a 5% leak, which is an unbelievably high leak rate, it would still only add about 1.6% of greenhouse gas contribute back to the atmosphere with hydrogen, increase emissions by 1.6%, even though we've had that massive size. So it's small, it has to be addressed. We have to minimize hydrogen going into the atmosphere. The last thing I'll mention is none of the analysis that we've talked about on atmospheric carbon cycling has really taken in full consideration some work that we did. Actually, I was involved in this almost 20 years ago, with that. In fact, most of the hydrogen cycle, the hydrogen is removed from the atmosphere, not so much by this process. This process is important, but most of the hydrogen, 80% of the hydrogen cycle, removes it by soil microorganisms. The soil microorganisms just love hydrogen. If there's hydrogen in the atmosphere, it will take it out and eat it. Is an energy source. And we've did some analysis, showed even small increases in atmospheric hydrogen stimulate the bacterial growth of these and pull the hydrogen back down again. So we have a natural sort of offsettings with hydrogen leaks that pulls the hydrogen back out. A lot more work needs to be done here. If there's any microbiologists or soil biologists, soil scientists on the call today, which is unlikely, I strongly encourage this. A lot more work needs to be done in this area. So finally, in conclusion, addressing climate change requires zero-emission energy carriers. Electricity is the most important one, but hydrogen, I would argue, is needed, as well as biomass and biofuels. The hydrogen markets, transportation, heat and power, export, didn't say much about export. We'll talk more about it in a future one. And hydrogen is more challenging to transport and store than incumbent fuels, but the real importance here is we got to get to scale. The only way we're going to address a lot of these problems is not do it in small things. We got to focus on hubs and corridors to solve this problem. Thank you very much.
Well, thanks, David. I'm sure a lot of us are going to have to go back and look at that recording and watch it a few times to fully capture all of the knowledge that you gave us today. Really appreciate that. So we do have a little bit of time. There's been some questions trickling in, which is great. So we do have a little bit of time for a few questions. One question I have is, what do you think are some of the really regional factors that make hydrogen a more applicable energy carrier than others? And I guess specifically, what are the unique characteristics in Alberta and the Edmonton region in particular that might make hydrogen an attractive energy carrier option?
Well, I think, Edmonton has the obvious benefit of it as a major producer of hydrogen already. It's not producing it as an energy carrier, it's producing it as an industrial feedstock. And there's somewhere between probably close to 2,000 to 3,000 tons of hydrogen every day that are being made in Edmonton, just in the Edmonton region, the Fort Saskatchewan region and the Alberta Industrial Heartland. And there's a possibility of taking a side, and Edmonton already has carbon capture and storage pipelines, and it's already doing some CCS. And there's potential for some of the best carbon capture and storage geology has been identified in that region. So I think it's an early starter. Southern Alberta has some of the best solar and wind resource in Canada. And it's some of the lowest cost, and I think there's a real opportunity there as well, the Lethbridge area, for example. And then all of Saskatchewan and Alberta, and even parts of northern BC, have pretty good geology for, very good geology for geological sequestration. In other provinces like Quebec or Manitoba or BC, a large hydro resource gives them a low carbon source of electricity. And by combining, I would argue, combining that with wind and solar that they can produce in those areas, one can actually increase the amount of electricity and see significant production of hydrogen that could meet from those sources. And certainly we've heard about Newfoundland and its ability. It's a fantastic wind resource in southern part of Newfoundland, and the possibility of large wind farms that would produce hydrogen, not only for domestic use, but for export. So I think each province of Canada has different challenges and opportunities. I guess Ontario, if you want to talk Ontario, there's some opportunities with nuclear and some work done at Ontario Tech University of a new thermal technology to convert thermal energy from nuclear into hydrogen directly without having to go through electricity. And that could be a significant opportunity.
So lots and lots of possibilities. Really appreciate that. One more question. I wonder if you could talk a little bit about some of the lesser talked about uses of hydrogen. We had a few comments about maybe talk a little bit more about how ammonia could fit in, or how hydrogen internal combustion engines might fit in.
Yes, okay.
How that might contribute to excess NOx, for example.
Yeah, no, I think excess NOx is an issue. Well, I mean, we got to figure out how to build, if we're moving towards a zero emission energy system, it's really important to have a pretty clear view of what you're trying to build. But a lot of the issue in energy transition planning is to think about how you're going to get there from here. And one of the challenges we have with a lot of the hydrogen vehicles is that hydrogen fuel cell vehicles are not widely deployed yet. We've got tons of diesel engines around, and there's a possibility of an interim transition, which is hydrogen diesel dual fuel, where you can actually burn hydrogen in a diesel engine. You don't get the drivetrain advantage that you do with the fuel cell vehicle. But what it does mean, though, is that if you run out of hydrogen because there's not a fueling station, you need to make a trip, your vehicle doesn't get stranded at the side of the road. It just switches back to being a diesel vehicle. And we see a real opportunity. I'll talk more about this in the next presentation I give, a real opportunity for hydrogen diesel dual fuel vehicles to help to build out the hydrogen infrastructure in Canada, both in Western Canada and Eastern Canada, by actually being a little bit less of a step for the carriers, a lower cost in the initial stages, it's higher cost later. But in the initial stages of moving to a hydrogen economy, we see some real advantages and are encouraging government policies to introduce and move this forward for hydrogen, and encouraging companies to start making and trialing these vehicles, as is currently being done with the Alberta Motor Transport Association. On the ammonia side, a lot of interest in ammonia. It's a dangerous gas. It's pretty nasty. I wouldn't want to be running it in a car or a truck down a highway, but on big ships or trains where it can be handled in scale, ammonia could actually be a pretty interesting zero emission fuel. It can be burnt in a combustion engine. You don't get the drivetrain advantages, but what you do get is the zero emission, and you get to use your existing infrastructure. And I think that has to be part of our as our transition plan, to think about it and to try to find ways of reducing some of the barriers to testing and deploying these technologies at scale.
All right. Well, I think we are at time. Apologies for participants that we didn't get to all of your questions. There were some really good questions. As I mentioned a few times, the recording and slides will be available on our website. Connect with us on LinkedIn, Twitter. Our website is erh2.ca. Thanks everybody for your participation, and thanks again, Dr. David Layzell, for sharing some knowledge with us. Everybody have a great day.
Thank you so much.